So, good afternoon, everybody. I will continue today on the lecture about mortality. And in the last class, I ended talking about the issue of comparing mortality indicators across societies, across populations that have different age structure. So, for example, if we simply compare the crude death rate of the US back in 2013, 8.2 deaths for every 1,000 people in the population, to the crude death rate from the United Arab Emirates or Qatar, you might think that the mortality is much higher in the US than in these two other countries. But some of this low crude death rate at the UAE and Qatar might be the result of a younger population compared to the US. The US has a bigger proportion of people in older ages, while these other countries have a larger proportion of the population in working ages and fewer people in older ages. So we cannot simply compare the crude death rate of countries that have different age composition. And moreover, we should not compare the death experiences based on the crude death rate, even for the same population in different time points. For example, in the US, back in 1960, it was estimated a crude death rate of 9.5. So 9.5 people die in the US for every 1,000 people in the country. It declined. It declined to 8.2 by 2014. But these numbers don't look like there was a huge reduction in the crude death rate in the US. Like this 54 years of interval, it reduced only from 9.5 to 8.2 deaths per 1,000. Exactly because the crude death rate does not take into account the age composition of the US back in 1940 and in 2014. The CDR is not capable of capturing the reduction in mortality when population becomes older. So when the population becomes older, older people are more likely to die. And although they're more likely to die, maybe the US is now experiencing overall lower mortality rates by age groups. But the crude death rate does not take that into account because we simply get the number of deaths in the country in 1 year divided by the size of population. We do not take age groups into account. And the US did become older between 1960 and 2014. So now we have a bigger proportion, a larger proportion of people in older ages, with at least 65 years of age. And one indicator about that is showing that the median age back in 1960 in the US was 25 years. And in 2014, it was 37. What is the median age? It means that back in 1960, 50% of the population in the US was older than 29 and 50% younger. In 2014, 50% older than 37, 50% younger than 37. So the population is getting older. Older people are more likely to die. But that doesn't mean that the mortality levels are increasing in the US. It's just because that population in older ages are more likely to die. So we should break down the mortality information by age groups in order to take into account the change in age composition in the US between these decades, between these years, okay? So whenever we are trying to compare crude death rates of different countries or the same country over time, and we know that there was a change in the age composition, we should not use crude death rates, right? The crude death rate pretty much just takes the whole population in the denominator, does not break the population by age groups. And we know that population members are not equally at risk of death. Younger people are less likely to die than older people. In infants, children below 1 year of age are more likely to die than children between 1 and 4. So we have to take these differences into account. The risk of death varies by age, sex, race, ethnicity, socioeconomic status, and others. Usually, whenever we try to compare population, like mortality levels between different populations, we usually break it down by age and also by sex, because older people are more likely to die, and also because men are more likely to die than women. And just to show variation of death rates by age, we can just get a typical measure to estimate death rates by age groups. When we estimate death rates by age groups, we have the age-specific death rates, also symbolized by the capital M, and the same notation in demography, right? MXN means the age-specific death rate or age-specific mortality rate. You can also use the term death rate or mortality rate. From age X to age group X plus N. So we can calculate that for specific subgroups of the population by age group. How do we calculate it? With the same idea. In the numerator, we put the number of people who died, but who died on that specific age group in that specific year, and the overall number of people in that specific age group in that population that year. And the denominator here, an approximation to the denominator as we have been talking already, would be the population, the mid of the year of people in a specific age group. We also multiply it by 1,000 because these rates can get really small values. And the N here is pretty much the width of the age group, and the X is the initial age on the age group that we are evaluating. So if we are estimating the age-specific death rate or the age-specific mortality rate for the age group 15 to 19, this is the way that I symbolize it. Would be M 15.5, meaning that we have the age-specific death rate for people between 15 and 19. 15 with a width of 5 years, including 15. So it goes from 15 to 19 completed years of age. Okay? And the 19 there includes even people who are 19 years old and 19 years and 11 months old, right? Everybody who did not reach 20 years of age. This is the typical age curve of mortality by age group. For all the countries, I mean, they vary a little bit in terms of the level, of course, but the overall pattern is this one here. Usually, the mortality of infants, those who did not reach 1 year of age, it's higher than children who reach the age of 1 through 4. So instead of doing the age group from 0 to 4, we break it down. We break it down the first age group. So this one has a width of just 1 year, and this one has 4 years. And then for the other ones, we use 5-year age groups. And depending on data availability, we can go up to 80 plus or 85 plus, and some countries can have even information about to groups 100 plus. All right, so it would be 85 to 89, 90 to 94, 95 to 99, and 100 plus. And just to do a zoom in here on this portion of the graph, you actually see some variation. Really high levels of mortality for children who did not reach the age 1. And once they reach age 1, the chance of dying decreases a lot. And then afterwards, with age, start to increase again, 35 to 39, and keeps increasing to older ages until everybody dies, right? And And this rate here is actually being multiplied by 100,000. But you could do also only by 1,000, as I showed in the previous slide. It depends on how you want to show this information on the vertical axis here. So the age curve of mortality has usually this shape, really high for infants, declines, and then start to increase again. The best measures to compare mortality across populations that have different age structure, they take into account this. They take into account that different age groups have different chances of dying. The first age group has higher chances than the following one, and then afterwards it starts to increase until older ages. And what we're going to talk is pretty much some techniques that estimate mortality indicators in which we take into account these different risks of dying by age group, and then we can compare the mortality levels across different populations. Okay? So that's what the exercise of standardization and the exercise of life table we're going to do now. Okay? So the first one, standardization. For the standardization, we're going to use the age-specific death rates, not the crude death rates. So we're going to use the death rates broken down by age group. Because we want to compare the mortality experiences of countries that might have different age compositions. We use the standardization to take into account age composition when we compare death rates among different countries, because different countries, some of them have a higher proportion of people in younger ages, some of them have higher proportion of people in labor ages, and some of them have higher proportion of people in older ages. And as we saw in the previous graph, the mortality rates vary a lot by age group. And with standardization, we can compare death rates for different countries or years. We cannot compare crude death rates for different countries or years. We cannot compare crude death rates for different countries or years. So just a correction here. Before comparing death rates for different countries or years, we need to adjust for differences in age structure, right? So we estimate age-adjusted death rates, and we apply these age-adjusted death rates to a standard population. So that's the exercise of standardization. The original crude death rates cannot be compared before doing standardization. After we do standardization, then we can compare the crude death rates for different countries or years. So best way to write this bullet point here, we can compare crude death rates for different countries or years only if we do the exercise of standardization, right? That's another way to write it too. Hey, we already know a really simple way to estimate a single indicator based on age-specific rates. Do you remember the total fertility rate? How do we calculate the total fertility rate? We estimated the age-specific fertility rate for women between 15 and 49 years of age, broken down by 5-year age groups, 7 5-year age groups. And since they are all 5-year age groups, the width of those age groups were equal to 5, we can just add all the age-specific fertility rates and multiply by 5. Then we get the total fertility rate. How do we interpret the total fertility rate? If a group of women experience the age-specific fertility rates, consider here from 15 to 49 years of age, they would have on average a specific number of children. And women can have more than one child, so it makes sense to have a total fertility rates of 2.1, 2.2. Could we not do the same for mortality rates? If we go back to this graph here, we could get this age-specific fertility rate before we multiply by 100,000. The width of this age group, here's 1. So it just be this one, this age, this rate times 1, which is the rate itself. This rate here times 4, because the width equals 4. This rate times 5, this rate times 5, all of them times 5, until we have to make an adjustment in the last one that has an open interval. Could we just not do that? Multiply each one of these rates by the width of the age group and then add them all with the same idea that we did for total fertility rate? Why can we not do that the same way for mortality? Because let's say if we had this measure of total mortality rate that we don't use, but if I calculate a TMR, total mortality rate, why would not make sense? Because the total mortality rate would say what? If I put a group of people experiencing those age-specific death rates, calculated for a country in a specific year, they would die on average 1.7 times, 2.3 times. That doesn't make any sense because we die just once, right? That's why we cannot do that same exercise that we did for fertility. So we have to come up with another set of mortality indicators that make sense demographically. Women can have more than one child, so yeah, a TFR greater than 1 makes sense. We cannot die more than once, so this hypothetical total mortality rate greater than 1 would not make sense, right? But we have to come up with a measure in order to take into account age composition of countries and compare their mortality levels. Because young populations tend to have low crude death rates and old populations tend to have high crude death rates. Older people have higher chance of dying. So what the age standardization does is that we estimate a variation of the crude death rate, a standardized crude death rate, that allows us to account for the age composition of these countries, and then we can compare the death rates among different countries. So then we can compare the crude death rates of different countries, even with different age composition, only if we do the exercise of age standardization. So the basic formula for that is pretty much you get the age-specific death rate for a specific country, and then the population in that same age group that we're considering here, divided by the total population, multiplied by 1,000. And of course, since you have several age-specific death rates, you have to add them all. But this proportion here of people, this is the proportion of people in each one of the age groups. So I get, for example, a country like the US and a country like Venezuela. And first, I estimate the age-specific death rates for each one of these countries. So taking into account the death rates for different age groups. And then for one of the countries, I use the distribution of the population of the other country. So I can recalculate the crude death rate of Venezuela by using this data here from Venezuela and this data here from the US. By saying what? If I have these mortality levels from Venezuela and I apply to a population of the US, how many people would die for every 1,000 people, right? And for the US, I don't have to change anything. But what I have to have is for both crude death rates, use the same proportional distribution of the population by age group. That's the exercise of age standardization. And I'm going to go with you step by step. So this is data for the US in 2006. The population in each one of these age groups, and here we have data up to 100 plus, 0 to 1, as I said before, 1 to 4. Number of deaths. If we divide number of deaths by population, we get the age-specific death rates. So we have here deaths divided by population, we get the age-specific death rates. This first one here, age-specific death rate, is the chance of dying of children before reaching age 1. So this specific indicator here is actually the infant mortality rate, IMR. That's the death rate of children before reaching age 1. And then you have the age-specific death rates for the other age groups. And you also, based on this first column here, you just add everything, you have almost 300 million people, 298 million people. And if you want to know the proportional distribution of this population by age group, how do you do it? You divide each one of the populations in each one of these age groups by the overall population. So how much is 4.1 million divided by 298 million? If you don't know how to do it, just read this slide, 0.0139. So this number divided by this is this one here. 16 million divided by 298 is 0.0548. If I wanted to have this proportion of the population actually percentage, I would simply multiply this by 100. So I would have 13.9%, 54.8%. Sorry. Multiply by 100. 1.39%, 5.48%, 6.75%. Okay? Since we just get the proportion varies from 0 to 1. If we add them all, we get 1. Here we have just a problem of rounding the data, but adds up to 1. Percentages vary from 0 to 100. For this exercise, let's just use proportion. So for now, which kind of data did I have to collect? I had to collect the size of the population by age group, and I had to collect the number of people who died by age group for that same country in that same year. How do we calculate the crude death rate? The original one. The original one, we don't care about age group, right? We just get the overall number of deaths, 2.5 million, and divide by the overall number of people, 298 million. If we divide 2.5 million by 298 million and multiply by 1,000, we get 8.41. So that means that back in 2006, for every 1,000 people in the US, 8.41 died. But we don't want to just compare this crude death rate with another country that might have a younger population. For example, Venezuela. Population by age group in the first column. The second column, the same exercise. We get the population, each age group, divide by the total size of the population. We get here a proportion of 0.0219, which means 2.19%. Proportion of 0.088%, and so on, which add up to 1 unit. Rounded it up to 1 unit. Number of deaths by age group, and the age-specific death rates by dividing this number by this number, you get this one here, and so on. The crude death rate, a simple one, how do we calculate? We just get the total number of people who died in that specific country in that specific year, 102,449, divided by 22.2 million. Multiply by 1,000, we get a crude death rate of 4.61. So for every 1,000 people in Venezuela, 4.6 died in that year. So it's already considering the size of the population. And look, 4.61 in Venezuela is lower than in the US, 8.4. Does it mean that the overall level of mortality in Venezuela is lower than in the US? No, not necessarily. Because we are comparing crude death rates of countries that have different age composition. When we say that countries have different age composition, is this column here. This column here in Venezuela has more people in younger ages. See here, 10%, 10%, 10%. In the US, it's only 6, 7, 7. In the US, in older groups, like 70, 2.8, 2.4. Here, only 1.3 and 0.97. So Venezuela has proportionally less people in older ages and more people in younger ages. And in younger ages, the chances of dying, we see here, these numbers here are lower than these numbers. Chances of dying at the older ages, see how much bigger they are. See, it's here, it's 0.00064, and here's 0.48. But they have not so many people here compared to the US. So the standardization process is going to take that difference into account. So just taking that column of the proportion and now multiply by 100. So for example, here for the US, this number here multiplied by 100, 0.0139, 1.39. The same thing for Venezuela, 0.0219, 2.19. And just get this all, and they all add to around 100%. Just to see how these populations have different age composition. I keep talking, oh, we cannot compare the original crude death rates for populations that have different age compositions. The age composition is this, or these two columns here. How do we compare these two age compositions? One way is to get this number and divide by this number, get the ratio of the proportion of the percentage of people in the US in this age group by the percentage of people in Venezuela by this age group. How much is 1.39 divided by 2.19%? 0.63. This number here, since the US is in the numerator and Venezuela is in the denominator, if this number is below 1 unit, we have a higher percentage of people in Venezuela in these groups compared to the US. 7.24 divided by 10, it's a number below 1 unit. 6.79 divided by 7.26, a number below 1 unit. And as we get older, we start to have higher proportion of people in the US in these age groups than in Venezuela. So a bigger number divided by a smaller number, we're going to have a ratio bigger than 1 unit, right? So in older age groups, we have more people in the US proportionally, and in younger age groups, we have more people or less people in the US proportion, more people in Venezuela proportionally. So the US has an older population than Venezuela. This is causing the crude death rate in the US be higher than the crude death rate in Venezuela. Cool? How can we just look at this information here in a graphical format, which is a little easier to look at? So let's just look at these two here. Let's put these two columns in a graph. US, blue, Venezuela, red. What do we see? For younger age groups, these are percentages of people in each one of these age groups in each country. In the US, for younger age groups, we have fewer people. In Venezuela, more people. For older age groups, then proportionally, we have fewer people in Venezuela and more people in the US. And then we can also get that other column here, the ratio, and do a graph with that one as well. That's this graph here. and I just put this reference equals to 1, would be the line in which you have exactly the same proportion of people in Venezuela and the US for a specific age group. Overall, what do you see? The ratio is below 1 unit, the ratio of US divided by Venezuela. If it's below 1 unit, you have more people in Venezuela than in the US proportionally. So more people in Venezuela proportionally in younger ages, and more people in the US proportionally in older ages. So here I'm just saying US and Venezuela have different age compositions. We should not compare the original crude death rates of these two countries. We should do standardization. So all this process here of showing these graphs is just to show that the crude death rate in the US is larger than the original crude death rate in Venezuela because of these differences in age composition. So this is age composition, this is age structure, okay? And the age-specific death rates, the age-specific death rates in the Excel file that's available in the course website, if you just zoom in to the age-specific death rates by age group, you're going to see here, because of the scale of the graph, they look like they're the same, but always Venezuela has a higher age-specific death rate than the US. And that's even more clear for older age groups. Where did I get this information here from? I just went back to the previous tables. For the US, I got this column here. For Venezuela, I got this column here. But look, 0.006, 0.016 higher in Venezuela, 0.00029, 64 higher in Venezuela, right? So the age-specific death rates are higher in Venezuela than in the US for every single age group. And that's what this graph here is showing. Like I said, in the Excel file, I zoom in this younger age group so you can see, you can better see the differences in a graph format. So we have to do this standardization. How do we do this standardization? This table. That's all. Pretty simple. So how do we do this? Let's go back to the formula to see what we have to do, right? Back to the formula that I mentioned to you. In this specific case, we're going to get the age-specific death rates from Venezuela and see, let's imagine that the age-specific death rates in Venezuela were applied to the American population, distributed proportionally by age groups. So how would it be that crude death rate of Venezuela using the US population as the standard? The US, I don't have to deal with anything because the population is always the population of the US. I have to change the standard population just for one of the countries. So, okay, I have to get the age-specific death rate for Venezuela and get this one here for the US. And then I compare this new crude death rate of Venezuela to the original one for the US. Could I do the opposite? Yes. I could get the age-specific death rate of the US applied to Venezuela. So that would be the new crude death rate of the US using Venezuela as the standard. And then I would compare to the original crude death rate of Venezuela. Let's go slow. Age-specific death rate of Venezuela using the US as the standard. How do we do that? We have to go to the table of Venezuela, get the age-specific death rate here, 0.0162. 0.0162. I go to the table of the US and get results from this column here, 0.0139. Remember, from Venezuela, I got from here. From the US, I get from here, 0.0139. 0.0139. What am I doing here? These are the observed age-specific death rates in Venezuela by age group. Right? Age-specific is already by age group. I got the number of people who died in specific age group divided by the population in each age group in Venezuela, got these rates, observed rates. Now I'm going to apply, let's imagine that these mortality trends, these mortality levels here were applied to the population in the US. Population in the US has this age structure, this age composition. So I pretty much multiply 0.01623 by 0.0139. I get these numbers. The Venezuela rates multiplied by the US proportional population. So I multiply, right? Back to the formula. I'm just multiplying. Then I'm going to add everything and then multiply by 1,000. Back to the table. I multiply each one of them. Now I will add everything equals 0.0097. And then I multiply by 1,000. So if I get the mortality levels in Venezuela, take into account the chance of dying by age group, and apply that, those chances of dying, mortalities from Venezuela. If I get that mortality from Venezuela, I apply to a population with the same age structure as the US, 9.68 people would die per 1,000 people in that population. Now, yes, I can compare this crude death rate of Venezuela with the original crude death rate of the US, because Venezuela is using the US as the standard population. So 9.68. I'm going to go back to this data. The original crude death rate in the US that we saw before was 8.4 deaths per 1,000 people. In Venezuela was 4.6. So we had the misleading information that mortality was higher in the US. But if we get the age-specific death rates in Venezuela applied to the population in the US as the standard population, we would have 9.68 deaths per 1,000 people. This is the standardized crude death rate in Venezuela using the US population as the standard. So this number now is higher than 8.4. So yeah, mortality is higher in Venezuela than the US, because now we standardized the rate, the crude death rate in Venezuela, and now, yes, we can compare the crude death rates between these two countries. This exercise here, in the first table, I follow the same procedure that applies in that formula, 7.4, that appears on page 171 of the textbook. So this formula here appears on page 171 of the textbook. So I just follow that same exercise. You can do a little bit different. You can get the standard population in the US without the proportional terms, get the observed rates in Venezuela. If you apply these observed mortality rates in Venezuela to this population in the US, you would expect 67,000 people in the US to die before reaching 1 year of age. If we add all these people here, 2.8 million divided by 298 million people in the US, this number divided by this multiplied by 1,000, 9.68. The result of this table is the same one as the previous table, 9.68. It's just a different way. Whatever you think it's easier to comprehend, you can do it in these two different ways. So now you can compare crude death rates of the two countries and know that actually Venezuela does not have lower levels of mortality than the US. Venezuela has higher levels of mortality than the US. Cool? Then we go to the second measure of mortality that allows us to compare mortality levels between countries that have different age composition, different age structure. And we use this tool called life table, which is one of the most important measures of the mortality experiences of population, because the life table will provide us at the end one measure that you for sure have heard about it before, the life expectancy at birth. What is the life expectancy at birth? Based on those age-specific mortality rates that we saw in the previous tables, if we put a group of people experiencing those age-specific death rates, how many years on average they would live? That's the life expectancy at birth. If you put a group of people experiencing those age-specific death rates from 0 until the last age group, how many years on average they would live? Remember that I said you could not get the age-specific death rates, multiply by the width of the interval, add them all, because we cannot die more than once. So what demographers came up was with this other measure, the life expectancy at birth, that actually measures how many years on average we would live if we were exposed to a specific group of age-specific mortality rates. And the development of the life table goes back to John Grant, the father of demography, in his Bills of Mortality, when he was using historical data from London, parish data from London, in which he broke down the number of people dying in each one of the age groups. So he was one of the first ones to look at mortality by age. And he also broke by sex, and he also broke it by urban and rural areas. So demographers use the life table to determine life expectancy. But what's interesting about the life table, it also tells, okay, in a specific country, in a specific year, if I'm exposed to these age-specific death rates, let's say that we estimate the life table, and I get that people would live on average 75 years of age. But if someone reaches age 15, that people had the chance of dying before reaching age 15, based on data for that country. But now that person reached age 15, how many years on average that person is expected to live, given that person is now 15 years of age, did not die before? The life table also gives us that. And it's going to give a number that's going to be higher than 60 in this example. Why 60 in this example? Because what was the number that I gave in the example here? The life expectancy at birth? 75. The person reached 15 years of age. So this person should have some additional years to live, since that person did not die before. It overcame the risk of dying, has more chance of surviving. So the remaining years of life will be, let's say, 62 plus 15, 77, which is more than 75, right? So the life table also provides that. Life expectancy for every single age group, not just for life expectancy at birth. Life table can be used also as the basis to do population projections. And we're going to talk about that as well. And the life table was already used by us in the net reproduction rate. The net reproduction rate that had to take into account the risks of mothers dying while they were exposed to the chance of having children, that big LXN column in the net reproduction rate comes from the life table, right? So, like the total fertility rate, the life table is a synthetic or hypothetical measure. So that's the same idea that I just said now. It tells us how many years of life on average may a person expect to live if that person, during his or her lifetime, is subjected to the age-specific probabilities of dying, of a particular country or population at a given time. So that person, we get the age-specific mortality rates. Based on the age-specific mortality rates, we calculate the age-specific probabilities of dying or mortality probabilities, right? We get the rates, transform it to probabilities. We keep doing some more calculations in the life table. We get the life expectancy at birth. How do you interpret life expectancy at birth? With the same concept of synthetic or hypothetical measure. If I expose a group of people to the age-specific mortality rates that we have in this country, from 0 until the last age group, those people would expect to live on average this amount of years, right? That's the same way as the total fertility rate. If we get a group of women and expose them to the chance of having children by those age-specific fertility rates from 15 to 49, they would have, on average, specific amount of children. So in the US, let's say that the population in the US had a life expectancy at birth of 78.7 years in 2010. This means that if a cohort of people throughout the years of life were subjected to the age-specific death rates of the total population in the US in 2010, the age-specific death rates calculated for the US back in 2010, they would live on average 78.7 years, right? Same idea as the total fertility rate, but now applied to mortality. And just to give you examples, how life expectancy varies across the world and also by sex. The average in the world back in 2013 was 69, more developed countries 65, less developed countries except China 65, Japan the highest, Lesotho and Sierra Leone one of the lowest ones. And in all these countries, women live longer on average than men, right? 69, 73, all women here living longer than men. So whenever we do life tables, we break it down for specific countries. Life tables take into account the age-specific death rates, and also we break it down by sex. Okay? Sometimes we have to be careful when we interpret the life expectancy at birth, and the symbol for the life expectancy at birth is the E0. We need to be aware of the fact that when we consider life expectancy at birth, infant mortality plays a very important role. When the life expectancy at birth is very low in some countries, a major reason is because the infant mortality, the age-specific mortality rate of that first age group, children below dying before reaching age 1, the infant mortality rate is high. So that puts life expectancy at birth in lower levels. When we compare values of life expectancy at birth across countries, and some of these countries have really high levels of infant mortality, we should not think as the life expectancy at birth as the usual age of dying, as the model age of dying, the age in which most of the people die at. Because the life expectancy at birth now is bringing lower levels influenced by the high levels of infant mortality. So we should not interpret life expectancy at birth for these countries as that age in which most of people die, because it could be a little bit higher. So we can look at the life expectancy at the next age group, of the age group between 1 to 4, or the age group between 5 to 9. Okay? And I'm going to show you where we look at this in the life table. The life tables are usually calculated for age groups, the same way as we did total fertility rates by age groups, in the same way as we just did the standardization. instead of getting information for every single age, we break it down by age groups. Whenever we have a life table that we break the population by age, we don't get information for every single age, we are estimating an abridged life table. And usually we break the population in 5-year age groups. But remember, the first two, it's 0 to 1, width equals to 1, and the second one is 1 to 4, width equals to 4. But the other ones, usually 5-year, until we have the last one, an open-ended interval. So we usually use 5-year age groups rather than single-year age groups, usually because of availability of data and also reliability of data. In developing countries, if you get information of death by age group, you can have a lot of information, a lot of variation because of problems in reporting the data, in missing data, and so on, underreporting of death. Even now during the pandemic, when you see this number of deaths by day due to the coronavirus, usually what most of the data sources do, they do the average of the 5 closest days, exactly to avoid all this variation. And the same idea here, if we just do this death rates by every single age, the example of the pandemic, I did it for every single day. Here, instead of doing for every single age, we group them in 5-year age groups. The same thing as we did for the standardization, using that age-specific death rates. And the way that it works, the life table, we get the age-specific death rates that we had, for example, for Venezuela and the US, and they exercised before. For the age group 0 to 1, 1 to 4, 5 to 9, until the last one. And what do? We apply that mortality to this hypothetical population. The hypothetical population should have the same size across the life tables that I want to compare. And this hypothetical size of the population that will experience those mortality rates, it's called the radix of the life table. And the radix can be a number equals to 100,000, or could be 1,000, or could be 1. The important thing is I'm comparing life tables from different countries. I have the age-specific death rates, the same unit of analysis. If I don't multiply one of them by 1,000, I don't multiply the other one. And the radix of the life table should be the same number, right? Usually 1, 1,000, or 100,000. And then from each age group to the next, we apply the mortality. Let's say that 100,000 people started to experience the age-specific death rates in that country. And then experience the first one, the age-specific death rates for people between 0 to 1. Some people will die. How many will go to the next one? You discount from this number. And for the next group, how many will survive to the next one? And then you keep going lower in that number. From each age to the next, the population is decremented according to the age-specific mortality rate of that country in that specific year. The mortality schedule is fixed and does not change over the life of the population. The idea is that we have this data for a specific year, in a specific population, a group of people is being exposed, and then you expose them to those rates estimated for that population in that specific year. This is the life table. So we first start the life table with a measure that's not showing here, and we already saw it before. The capital MXN, which are also symbolized by the ASDR, the age-specific death rate. Also age-specific mortality rate. Based on the age-specific mortality rate, I calculate the age-specific probability rate. I messed up everything. Based on the age-specific mortality rate, I estimate the age-specific mortality probability. From rate of mortality, I calculate probability of mortality. And there is a formula to do that transformation that I'm going to show you in the Excel table. Right? So we have here, how did we get it from? How do we get the mortality rate again? The mortality rate is like the exercise in Venezuela and the US. You have the number of deaths for each one of these age groups, the population in each one of these age groups, divide one by the other, mortality rate. And with this transformation, with the formula that I'm going to show you later, you pass it from rate to probability. What's the difference between rate and probability that we discussed before? The rate, the denominator of the rate, is the number of person years, the number of people actually exposed to the risk of the event measured in the numerator, in this case, mortality, the number of people at risk of dying. Since it's hard to estimate person years, what's an approximation of the denominator for rates? The population, the mean of the period. So the denominator of rates is the population, the mean of the period. What's the denominator of probabilities? The population at the beginning of the period. So the denominator of rates would be the population in July 1st. The denominator of probabilities would be the population in January 1st. The numerator is the same thing. It's the number of people dying in that specific age group. So from deaths in population, we get mortality rates. From mortality rates, we get mortality probabilities, the QXN. And then we start to expose a group of people to those chances of dying. If we have 100,000 people being born, and we expose to this chance of dying between the ages of 0 and 1, if I multiply this number by this number, I get 612 people dying. Right? I have the probability of dying multiplied by the radix, the little lx, the little l 0, 0 because that's the first age group here, going from 0 to 1. This number multiplied by this number, 612. So 612 people would be expected to die if this amount here are exposed to this rate before they reach age 1. So 612 people die before reaching age 1. So how many people reach age 1? 100,000 minus 612 is 99,388. And then we get 99,388 multiplied by this probability of dying. So we expect that we would have 106 deaths of people between the ages of 1 to 4. This amount of people reached age 1. Some of these people will reach age 2, some of them will reach age 3, some of them will reach age 4, some of them will go on to other age groups. But some of them will die before. How many of them will die between the ages of 1 to 4? 106. So how many will reach at least 5 years of age? This number minus this number, 99,281. And I keep doing the same thing. Multiply this, get this number, this one minus this, get the next one. Until the last age group in which everybody dies. Right? 100%. Everybody dies. So this 1,968, everybody will die. This number multiplied by 1, 1,968 people will die in the last age group. Cool? Look, the big L, XN column That's the column that we use for the net reproduction rate in the fertility chapter. What's the meaning of this column here? This 100,000 people here, not everybody reached age 1. Some people died at the age of 1 month, at the age of 2 months, 3, 4, until 11 months, right? So in total, these 100,000 people, they lived a total of 99,465 years. So that's what it's called person years. If nobody had died, 100,000 babies had survived to the next age group. One baby survived 1 year, the other one 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 1 year. If we add everybody, how much would have been the big LXN? 100,000. Let's say that everybody survived. Nobody died here. This number minus 0 would be 100,000. Let's see that also this probability of dying is 0. Nobody dies here up to here. So let's say that nobody's dying. Here we have 100,000 people and they will reach 100,000 people. If we have 100,000 people here and 100,000 people reach the next one, how much would be this number? If we had 100,000 people reaching exactly age 1 in the second column, in the second row of the little LX, 100,000 people reach age 1, and then 100,000 of them reach age 5. What does it mean? That all these people here, 100,000, lived throughout the whole interval of 1 to 4. What's the width of this interval, 1 to 4? 4. 4 multiplied by 100,000, this number would be 400,000. Let's just go a little bit further. This number here, let's say that there is no mortality. And these people here, 100,000, will reach at least 10 years of age, 100,000. So these people here, everybody lived from 5 to 9 and reached age 10. Width of the interval, 5 to 9, 5. 5, 6, 7, 8, 9. 5 years. Everybody lived throughout these 5 years, so everybody lived 5 years. Multiply by 100,000, we should have 500,000. Why is this number below 100,000? Why is this number below 400,000? Why are these numbers below 500,000? Because people are dying. People are dying, so these numbers here start to decline. So this big LX and column is showing us how many years in total those people are living in each one of these age groups, the number of person years. If I survive from 5 to 9, I'm one person, and I reach age 10, I would have contributed 5 person years because I lived from 5 to 9. That's why we would multiply by 5. And then these are the overall number of years that people live throughout each one of these age groups. The X column will do the cumulative result going from the bottom. So getting this number here. I get this number here. This number is the last one, so I will just repeat it here. 29,000 here is going to be 24,000 plus 4,500, 29,000. How did I get this 108,000 here? 108 is 79,000 plus 24 plus 4. This number here, this plus this plus this plus this, until we get here. What is this number? This one plus this one plus this one plus everything here. So what does this TX mean? Let's say that we went to population this classroom here, and we calculate how many person years we all live. So here we have 3, 6, 9, 12 people, including me. So our radix is 12. The little L0 here is 12 in this example. And then I will follow this group of people here. And I didn't see someone in the back, so it's 13 people. No, wait, 3, 6, 9, no, 12, that's right. I will follow everybody here throughout their lives and write down how many years you lived overall. If I get the overall number of years that you get, that you survive, if some of you will reach age 60, 65, 70, 100, I will just get these numbers. When you die, add them all. When I add them all, is the equivalent to this number here. If I want to know from this example that I just gave here, for this group of 12 people, and I add all these numbers, how do I know what was the average age until which people lived in this example? Let's say that the number was 700. What do I do? Sorry? Divided by the number of people in the room. 700 divided by 12. That will give the average number of years that we lived. Some of us died younger, some of us will die later. Where is this information in the life table? What do I have to do to get the same? Which number I divided by which number? The overall number of years is which one in the life table? $7.8 million, right? This number. 7,866,027. The overall number of years that this population will live if they were exposed to these probabilities of dying. To get the average, I divide that 7.8 million by what? By the radix of the life table, by the number of people who were born, that started. 7.8 million divided by 100,000, 78.7. Simple, easy breezy. I'm not expecting you guys to memorize the formula to calculate the probability of dying based on the mortality rate. I'm not expecting you guys to memorize this formula for the big LXN. I want you to understand the logic, because the formulas, you can apply them afterwards using the Excel spreadsheet. But what is interesting is that now we have all these measures of life expectancy at birth here, 78.7. What does it mean, 78.7? If I get a group of people here at the beginning, if I get this group of people here and expose them to these chances of dying, they would live on average 78.7 years. Cool? Even if this number was equal to 1,000 or 1 unit, as we saw before, then the TX would be also proportional, would be a smaller number. So this number divided by this would be the same. if we have the same age-specific probabilities of dying. But if I survive a little bit to older ages, so if I survive to age 10, 69.3, what this number here means? That's what that thing that I mentioned before. That's the life expectancy at age 5. It means that if people, no, sorry, at age 10, that's the example that I'm giving here, age 10. If people are exposed to these chances of dying before age 10, but let's say that they don't die, they keep surviving, and they reach age 10. Once they reach age 10, how many more additional years on average they would expect to live since they overcame the risk of dying at younger ages, but they didn't die? So they would live on average an additional 69.3 years. If I'm 10 years old, how many years am I expected to live more in total? 10 plus 69, 79.3. 79.3 is higher than 78.7 at the beginning of the table, because here I get a credit, I get a bonus of life because I didn't die before. At age 70, if I had the chance of dying before age 70, but I didn't die, how many more additional years than I'm expected to live? 15.5. So on average, how many years people who reach 70 years of age will live? 70 plus 15.5, 85.5. Wow, that's a good credit. 85.5 compared to 71.7, 78.7 at the beginning of the table. 85.5, 78.7, because these people here overcame all these chances of dying, they didn't die. So they will still have 15 years on average of more life, which means 70 plus this 15.5. And this extra column that I'm doing is pretty much adding column 7 of the life expectancy for each one of the age groups with, I'm just add that one to the age at the beginning of each one of these age groups here, right? So it's 10 plus this, 15 plus this, and so on. So I can add a column which would be the EX plus X, X being the beginning of the age group, the age of the beginning of the age group. So this is the life table. So the life table, I pretty much get the age-specific mortality rates, transform them into mortality probabilities, calculate the average number of years. And this number here is kind of like that. I follow you over your lives. I see when you die, get the age of you all divided by 12. That's how the life expectancy of these 12 people here. Right? The next slides is pretty much explaining what I just did. The QXN is probability of dying between age X and age X plus N. LX is the number of survivors at each age X at the beginning of the interval of that age group. Why this number here, or this notation here, has QXN? That's the probability of dying between each one of these age groups. This is the probability of dying between the ages of 35 and 39. Why here we just have LX, not LXN? Because this is the number of people surviving to the beginning of the age group, the number of people surviving to the age 5, number of people surviving to the age 10, number of people surviving to the age 15. Why D has the XN? Because this is the number of people dying between these ages. 10 to 14, 70 people die. 15 to 19, 244 people die. This also is the number of person years that people are living in between these ages. Here's the cumulative number of people, number of years that this group lived, for example, from here, from 0 to the end, from 1 to the end. And the EX is also the X because I'm saying, when I'm at age 0, what's the average number of years that I'm expected to live? When I'm at age 1, how many additional years I'm expected to live, to survive? When I'm at age 5, how many years am I expected to survive? Right? So what I'm going to go in the next class is pretty much explain this, and I will show in Excel both the exercises of standardization and life table, just to show you how these calculations are done. And here in the life table, I will just explain each one of them. And all this portion here afterwards that is marked as extra, I will not go in detail over it. I will jump it into the next topic of the chapter. Okay? So 2 p.m. now. Thank you very much. And I see you guys on Thursday. And quiz 13 is open now in Canvas. Thank you.